So this video is an example of the Buckingham Pi theorem, which is used to reduce the number of variables that we need to describe a problem. This worksheet is something you can download from the course webpage or from the link in the video if I'm able to find a way to host that. What we want to do is design a pipeline. And so what I really mean there is that we need a pump that's going to overcome the shear. And really what we want to do is make this as useful as possible, and so we're going to find this pressure caused by shear, and we're going to take that pressure drop and we're going to do it per unit length. And so for any length pipe we could figure out what we need to do. And so step by step the process of applying Buckingham Pi looks like this. First we're going to list all of the variables involved in the problem. This is the hardest step because we kind of have to understand what's going on already, or we can follow this checklist here. So geometry of the system, this is a pipeline, so things that are interesting look like diameter and length. Fluid properties, what do we use to describe a fluid? Well, in general we're going to use viscosity and we're going to use density. And then external effects, we want this flow to move at some speed, v for velocity. And so let's write these now as a final list, and we're actually, because I said we're interested in the pipe per unit length, we're going to combine a couple of these things. So we're going to have delta P over L, and we're going to write this as a function of diameter, density, viscosity, and velocity. Okay, that's step one. Now what we want to do is express each of these variables in its basic dimensions. And so let's use the force, length, and time system, okay? And I want you to notice that this delta P over L, we're counting as a single variable rather than two. This is one number. So we're going to actually write that as a single number. Lowercase l here, like so. All right, so what's pressure? Well, pressure is force per area. So that's force, area is length squared, but it's on the bottom, so it's L to the minus 2. And then that's the pressure divided by L, which that's another length, L to the minus 1. And so that whole thing looks like F L to the minus 3. We're going to repeat that for all our variables. So we got diameter D, well, that's a length. We've got density, rho. Density is mass per volume. Remember that volume is length cubed, and since it's on the bottom, it looks like this. But we're not using the mass length time system, we're using the force length time. So we got to switch. How do you do that? Well, we're going to use F equals ma to do that. We can solve that for m as force per acceleration. And so force, well, that's already the base dimension. Acceleration looks like length per time squared, except it's on the bottom, and so we get t squared here over L. And so we can write then that mass is equal to force length to the minus 1 time squared. And so we replace this mass with that we just came up with, and it gives us force length to the minus 1 times squared, and then the length to the minus 3 that we started with, and so we can simplify that a little bit to be mass length to the minus 4 time squared. Next variable is viscosity mu. It has, for this one I usually just go look up the value and see what the units are on it. It turns out to be force per length squared times time. And lastly we have the velocity. Velocity is distance per time, length per time to the minus 1. Okay, so what we've done is just written the units out, or the dimensions, excuse me, for all of our variables. The next step is to do some counting. So how many variables do we have? Well, we've got 1, 2, 3, 4, 5. Remember, we're treating delta P over L as a single variable. So we got 5 here. R is the number of base dimensions. We used all 3 of them. Here's a force, here's a length, there's a time. They all showed up in this one, so that's 5 minus 3 tells us that we need a total of 2 pi terms. And so what we want to do is first pick the repeating variables. How many do we need? Well, that comes from r, the number of base dimensions here. And so we need 3 repeating variables. Things we don't want to use as repeating variables are the dependent variable. That's the thing we're most interested in. We only want that to show up once so we can get it on the left-hand side of the equation. So we're going to leave delta p over L out of our consideration here, which means that our options for the repeating variables are everything else. That would be the diameter, the density, the viscosity, and the velocity. What we want to do is pick the simplest set of independent dimensions that we can find. And so, for example, the diameter is gives us a length. The velocity gives us a length per unit time, so that brings in the time. And then the density gives us FL to the minus 4 T squared. So what's interesting about this, right? This is kind of a variable that represents our length, the diameter is. The velocity brings in the time for us so that we have a variable that captures the time which we need. And then lastly, we had a choice. We could use viscosity or density. We ended up picking density as a thing that represents the force. And so this variable, these 3 variables contain the 3 base dimensions that we're interested in, but they're also independent of each other. There's no way to mess around with velocity and turn it directly into a length. Okay, here's why that's useful. Now that we've got this, we can form our first pi term, okay? So let's go ahead and grab, we're going to call this thing pi 1, and it's going to be one of our non-repeating variables. Well, we have 2 of those. We have this term here as a non-repeating variable, and we didn't use viscosity as a repeating variable, so those are our 2 non-repeating variables in this problem. So we're going to write it then, our first non-repeating variable, delta p over L. Oops, sorry, that should be a lowercase l over L. And we're going to multiply it by our 3 repeating variables, diameter, velocity, density, d, v, rho. And we want to give those their own exponents. So let's just call this A, B, and C. And now we're going to sub in the dimensions of all of these things. That's what we worked on up here in step 2. So delta P over L looked like FL to the minus 3. D has units of dimensions of length, so that's L to the A. Velocity looked like a length per time to the B. And density looked like FL to the minus 4 T squared raised to the C. And now, oops, that's a little sloppy. Let me get a bit better C here. C. And this now is where this becomes useful. We want pi to be dimensionless. And what that means is that all the forces have to cancel out, all the lengths have to cancel out, and all the times have to cancel out. Well, we can just write an equation for each base dimension to get that. So for example, the exponents on force. Here we have a force to the first power 1. And if we go through, the only other term that has a force is here, and it's raised to the c. So 1 plus c has to equal 0 if this is going to be dimensionless. Length. We get an equation for length that looks like minus 3 plus a plus b. So here's L to the b, and then this one is to the minus 4 times c. So minus 4c, and that has to equal 0. And lastly, time, if we go through, we have a minus 1b, and here we have 2c plus 2c, and that has to equal 0. So now we can solve these, right? This one up top tells us that c is equal to minus 1. We can plug that into the time equation. Sorry, this should just be a colon, not an equal sign. And that tells us that b is equal to minus 2, if you put the minus 1 in here and solve for b. And then we put those values for a and b into the length equation, and that lets us solve to find that a is equal to 1. And so now we come back up here and we say pi 1 is equal to delta p over L. Sorry, that's delta p over lowercase l. We got d to the a is 1. We got v to the b, which is minus 2. And we've got rho to the c, which is minus 1. And so our first dimensionless term looks like delta p over L times d over rho v squared. That was the whole point of this. Now we're going to do that in step 6 for a second time. This time we're going to use the other non-repeating variable. Remember, our first non-repeating variable was delta p over L. The only one that's not left is viscosity, so that's our other non-repeating variable. So we'll try this one more time. We're going to write now, called the first one pi 1, so we'll call this one pi 2, and it's going to look like mu d to the a, v to the b, rho to the c, just like we did here. These are the repeating variables. Only the values of a, b, and c are going to change. Again, we're going to sub in the base dimensions that we figured out in step 2, so fl to the minus 2 times t, l to the a, lt to the minus 1 to the b, and fl to the minus 4 t squared to the c. This lets us write some equations. Let's write an equation for force. So force, this first term has it to the power 1. It also shows up here to the power c, so 1 plus c is equal to 0. We've got length, which looks like we've got the first term here, a minus 2. Second term has an a. Third term has 1b. Fourth term has minus 4c. That has to equal 0. And lastly, our time. Well, time shows up there as a 1. Time shows up here as a minus b. And it shows up here, t squared to the c, so that's plus 2c, and that equals 0. So again, we solve these equations. This one tells us that c is equal to minus 1. I can take that, plug it in down here, find out that b is equal to minus 1, take those two values, sub it into this equation, and find out that a is equal to minus 1. And so that lets us write that pi 2 is equal to mu times d to the a, which is minus 1, v to the b, which is also minus 1, and rho to the c, which is minus 1. And so that lets us write this as mu over rho v d. So now we have two pi terms. We know we're done because up here we said we've got 5 variables minus 3 base dimensions equals 2, so we need 2 total pi terms. All right, so check to make sure they're dimensionless. I'll let you check your own work. I know I did it right, so I'm just going to leave that alone. The last thing we want to do is find out if there's anything that we could rearrange to use customary terminology. So for example, if you look closely, this may look familiar to you. Pi 2 is actually the inverse of the Reynolds number. And so what we can do is just replace it with the Reynolds number, and all of this still works because it now changes the final graph, but the relationship is still captured, and so it doesn't matter. So we're going to change pi 2. Instead of using what we came up with, we're going to just use the actual Reynolds number because that's more customary. And so now all we have to do is express the final form as a relationship among the pi terms. So for example, we said we want something that looks like this. Pi 1 is some unknown function phi of pi 2. Pi 1, remember, was delta p over L times d over rho v squared, and that has to equal some unknown function phi of the Reynolds number, rho v d over mu. And that's the end. A lot of people aren't comfortable with this because we don't actually have an equation yet, right? We don't know this function phi that makes this all work. And that's okay because what we're going to do next, or what we would do next, is we'd go do an experiment. And so we do some experiment to find this thing, and that would give us, delta P over L times the diameter over rho V squared as a function of the Reynolds number, and we'd get some curve. And if you did that experiment and built this curve, you'd be able to then use that for any fluid as long as you calculated yourself in terms of Reynolds number and this whole thing. Now, why is that useful? Well, once we have a value, let's say we're done, we've got this graph, we can say, well, we're going to make a pipe that has a Reynolds number here. That comes over here and tells us that this now is equal to some number, delta P over L times D over rho V squared is equal to an actual number that we plucked off of here. We can now invert this definition and solve for delta P over L for our particular situation because we know the diameter, density, and velocity. And it actually tells us, the thing we wanted to know, but it works for now, any fluid. Okay, so just a quick recap. What did we do? First, we listed all the variables. We wrote those variables in terms of their base dimensions. Then we said, how many groups do we need? Well, it's the number of variables minus the number of base dimensions that we used. And now comes the trickiest part. We want to select repeating variables that we're going to use in all of our pi terms. So what were the conditions for that? Well, first off, not our dependent variable. And second, they need to be independent of each other. So all of these were potential candidates. We picked D, V, and rho. Each one of them brings one more base dimension with it. So this one brought length, this one brought time, this one brought force. But they're all independent of each other. In other words, you couldn't use two different velocities and make this work. Then what we do is we take our non-repeating variables, the delta P over L and the viscosity, and we multiply them by our repeating variables to some power. And then we just solve for those powers so that the whole cluster becomes dimensionless. We did that for each of our pi terms, and we checked to see, and we discovered one of our pi terms was actually just something that's already been done, so we stopped messing with it and used the common term. And that lets us finally express our thing in terms of this. And so we took a function of 5 variables, turned it into a function of 2 variables, which makes it much simpler to go out and do the experiment and find that relationship. And so we just saved our boss a whole bunch of time and money, and he's very pleased with us.